Okay, so page 7.5. On Monday, I introduced the heat engines, and I said that the second law of thermodynamics is really introduced through the use of the heat engines. And in a way, we had to start looking at entropy as well. We didn't go into details, and we didn't really look at any equations in particular, but we redefined the meaning of entropy as a physical property. I also talked about very interesting cycles, two interesting cycles. One was a Carnot cycle, which you can see actually on this page, represents a refrigeration system. And the other one was a Rankine cycle, which represents typical power plant type of cycle. Now, we stopped at this point where we talk about reversible processes. Now, I want to talk about, I have mentioned reversible a lot of times, and this is when we start looking at what it really means and why actually even do we have to bother about looking at reversible cycles or reversible processes. So, an obvious example, a typical irreversible process is if you have a cup of coffee or tea, for example, and you leave it for about 5 minutes, it gets cold, and regardless of how much you wait, it's not going to gain temperature and heat again. That's quite obvious. So it's a sort of a one-way process in which you lose some heat and you can't reverse that process. So that is, that's quite obvious, and it's irreversible. A reversible process, on the other hand, is a process in which, regardless of whether you go forward or backward, there's no direction really. I mean, when I talked about the irreversible process of the coffee, there was one direction, and that was the direction of time. Now, if there is irreversibility, that doesn't really matter which direction you go. Why? Because in order to ensure reversibility, this is just getting a bit confusing really. So in order to ensure that you have a reversible process, you need to make sure that your process is done at a very slow pace. And we've been repeating that a lot, and it means that you need to really have an infinitesimal amount of amount of time really spent on. So you have to have time steps which are very small. Therefore, it takes a very long time. And if that is the scenario, then you're going to have a reversible cycle. I think the best way to demonstrate what really a reversible and irreversible cycle or process is, let's just look at the figure on page 7.6. So, what we're showing here, imagine you've got case A and case B. You've got two bags which you can inflate. Essentially, by inflating, it expands, and then by deflating, it sort of contracts, obviously. In the first case, what happens is that by expanding the bag, you have enough energy to overcome the resistance of the mass. Essentially, you are overcoming the gravity in this case. And by expanding this, you're lifting off, or you're essentially lifting this mass from its initial state. So you are gaining some potential energy. In the second case, by inflating this bag, you are now pushing this mass on a surface. In the first case, assume that all the instruments and all the parts in this system are frictionless, so that you don't have any losses, for example, in here, or there's no friction in between any of these components. In this case, you can assume the same. The only thing which you can't in this case, we're going to assume that the friction of the surface is still there. So we can't neglect the friction on the surface, but anywhere else you can assume that all the components are frictionless. So, imagine you inflate this bag. In the first case, your mass is lifted. If you then remove that energy, then naturally what happens is that because of gravity, the weight will come back, will essentially come down, and the process will be reversed. You don't have to have any external force applied to the system A in order to reverse that cycle. Yes, of course, originally you had to inflate this bag, which means that you had to have some sort of energy to inflate it. But as soon as you stop that energy or that force or whatever that is, this cycle and this process will go back to its original state. What about the second case? The second case, by inflating this bag, you've pushed forward this mass, and like the cup of coffee example which I gave you, regardless of how long you wait, this mass is not going to come back to its original state. Now, what's the subtle difference? The difference between these two examples are really in the orientation of the two masses. One is working in the vertical direction against the gravity, the other one is working against, on a horizontal surface, and it's working against friction. In the first case, no heat will be generated. In the second case, however, you're going to have some heat generated through friction. Whenever you have friction, you're going to have some amount of heat generated. Even though it might be very small and it's very difficult to measure, still the temperature of this surface and this mass is going to be increased very little. But that is enough for you to lose that energy and not be able to come back to its original state. So, in simple terms, this is an irreversible process, while this was a reversible. Now, something to emphasize is, I mentioned about the external effect or external force. What does it really mean? Well, in the case of A, or in system A, in order for the system to go back to its original state, you didn't have to use any energy from the surrounding. It just came back as a result of gravity. In the second case, if you want to go back to the original state, therefore moving the mass to position A, or position 1, whatever you want to call that, you need some external force. Something or someone has to push this back, which means the surrounding now has to do some work on your system. Which means energy has to be withdrawn from the surroundings in order to return the system to its original state. Therefore, this is exactly what we mean by an irreversible process. This still doesn't violate the conservation of energy, because the energy in the universe as a whole has been conserved. It's just the character of energy has changed, because you've now generated heat which has been dissipated into the surrounding. So, one question that you might think now is that, in reality, no process is really 100% reversible. So why do we have to even bother about the whole reversible assumption and all the whole concept? To answer that question, like a lot of other assumptions that we've been making, like for example, we've been talking about equilibrium. We said, in every problem that we've been looking at, we assume that the process is at equilibrium. And you might wonder, why do we have to do that? Because in reality, that's not the case. But because this is fundamental thermodynamics, you need to make some assumptions in order to be able to demonstrate some of the basic concepts and some of the fundamental equations. And in order to do so, you need to put those caveats in place. And it's the same thing with the reversibility. This reversibility essentially puts some limits on the physical processes, as we'll see later on. So therefore, it is actually important to know the effects of reversibility. And the fact is, even perfect heat engines, so now we're going back to the concept of heat engines, they have thermal efficiencies of less than 1, which means even perfect, what we mean by perfect, you know, if all the components of the heat engine are reversible, still the efficiency will be less than 1, as we'll see actually today. And as a result, these limits would serve as some sort of guideline for us. Something which refers back and confirms what we've been saying about these two examples here is the last paragraph. As, if you like, as an indication of whether your system is irreversible or reversible, you can look for something which involves heat transfer. When you have heat transfer in your cycle, it's a very good indication that probably that heat has come from, for example, frictional processes or frictional losses. And if that's the case, then it just shows that you have an irreversible process. So whenever you have friction losses, you would have irreversibility, like the second example in here. That's just one sign which allows you to identify an irreversible process. The other thing I would say is that it also matters what is the temperature difference. Now, remember in the context of heat engines, we were talking about reservoirs, and I said reservoirs actually are quite important. So, if the temperature difference in your heat engine or in your problem is a finite quantity, which we indicate that as delta T, which means you can actually sort of measure the temperature difference. You can see the change in temperature in that example. If that is the case, then you will have, again, an irreversible process. So whenever you have a finite difference in temperature, or finite quantity in terms of temperature, delta T, then you have an irreversible process. On the other hand, if you have dt, which it really indicates a very small temperature difference, in that case, you will have a reversible process. I think that paragraph is very well demonstrated in this figure on the next page, where you can see that the heat between, or the temperature difference between the two reservoirs, hot and cold, in the first case is irreversible because of delta T, and in the second case it's actually reversible because you have dt, which represents infinitesimally small quantity. So we did introduce, to some extent, very briefly, the reversibility and irreversibility of the processes. We now want to go back to the heat engines and to the cycles and the whole engineering aspects of the heat engines. And we want to look at the actual reversible heat engine. So, looking at the most obvious choice of heat engines, this is the direct heat engine that we looked at. We're going to make 3 assumptions. 1, 2, 3. These assumptions are necessary for our heat engine to be reversible. So the first thing is that we assume that the heat supplied to the top of the engine, and what I mean by the top of the engine is this one, that's the inlet of the engine, will be at temperature T1. What is T1? T1 is actually the temperature of the hot reservoir. So this and this are equal to each other. Assumption 2 is exactly the same, but corresponds to the cold reservoir. So it says, essentially the temperature which is rejected from the heat engine at the outlet of the cycle will be the same as the temperature of the cold reservoir. This essentially means that you're not going to have any losses from this point to this point. So from the hot reservoir to the heat engine, there's not going to be any loss. And the same from the heat engine to the cold reservoir, there's not going to be any heat loss either. Going back to the example of the power plant, which I gave in the last lecture, and I said, for example, the hot reservoir could be the core of the nuclear reactor, the cold reservoir could be the lake or the pond or the sea, whatever that is, close to the power plant. And you can imagine now, by this assumption, we're saying that all those pipe works and all those connections and all those instruments and components that we have in the system, they have to have no losses in order for the cycle to work. And the third assumption is that the engine itself is externally reversible. Why? Because the heat transfer which we've seen here from the reservoirs are essentially perfect. So that, there are no losses, and therefore the heat engine and all the external components to the engine are reversible. Which means there's not going to be any finite difference, finite temperature gradient in our heat engine. So these are the three assumptions for a reversible heat engine. This also means that the heat engine itself has to be internally reversible. So it's not all about external to the engine. The engine itself, and what I mean the internal components, I mean the valve, the compressor, the pump, the turbine, the heat exchangers, boilers, evaporators, those components within the heat engine, they have to be reversible as well, which means no losses. For example, no pressure waves or pressure drops across valves, or no friction whatsoever. And once you satisfy these conditions, then you have a reversible heat engine. Now, I want to look at some of the statements related to the second law of thermodynamics. These are important statements or extensions of the second law. The first one is the Kelvin-Planck statement. This is from 1920s. Not that you really care, but this is just to give you a time scale, because we've got more statements, and I just want to give you an idea on the time scale and the history of these things. So this statement says that it is impossible for any device that operates in a cycle to receive heat from a single reservoir and produce a net amount of work. So graphically, this statement suggests that this is not possible. You have to have this in order for your heat engine to work. Can you think of any, well, obviously we know that this satisfies the first law because there's a balance between Q1 and W, and that satisfies the first law. But do you know why that sort of system cannot work? Can you think of any example? Remember those three examples which I gave you on Monday, and one of them was that ship which was on the sea, and I said, well, the sea or the ocean has megajoules of energy, but you can never extract that heat and convert that into work. That's exactly that sort of example. So this could be the sea, this could be the ship, and you can never extract that heat from the sea, convert it into useful work. So this statement here, the Kelvin-Planck statement, leads to some important observations. And these are sort of some generic observations about the second law. The first thing is that the second law is a fundamental physical feature of work-producing machines. It tells us something very physical and very fundamental about machines or systems which produce work. Therefore, they have direct relevance to heat engines, because heat engines essentially are machines which produce work. The second thing about the second law is that it's an observational law. Which means you can actually you can see the effects of that in reality. It's not that it's only theoretical stuff. You can see and observe the effects and implications of the second law. And the third thing is that there is huge amounts of experimental evidence to support the second law. Those experimental evidences really are beyond the scope of this unit, but there are loads of examples where which are essentially proof of the second law. So these are some important features of the second law of thermodynamics. I think in summary, what you could say is that the net work done by a heat engine will be equal to the net heat supplied, and this means that Q1 minus Q2 is equal to Ws. So the net heat supplied will be Q1 minus Q2, and look at Q1, Q2 in this context. And the gross heat supplied is bigger than the net work done, which means Q1 is bigger than Ws. And it is true because you couldn't see that based on the first law, but it is true, and that's why you would have some sort of waste in the form of Q2 in order to balance both sides of the equation. Now I want to look at another statement, which again refers to the second law. This is the Clausius statement, and this is from 1850s. So that actually came before the Kelvin-Planck. Now, it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. This essentially refers to the reversed heat engine. Not the reversible, this is the reversed heat engine. This is the one which was opposite to the direct heat engine. This is what you would get in a refrigeration, or this is what you would get in a heat pump. And essentially it's just saying that if you've got, let me just draw it here. If you've got a cold reservoir and you've got this heat engine and you go to the hot reservoir, you can't not have any work out of this heat engine. Something has to be done. There's going to be some sort of work, positive or negative. And we know that's true because in a refrigeration cycle, you need to supply the heat engine with some work. Otherwise, you're not going to be able to achieve this cycle. Okay. Now, we want to start looking at the definition of efficiency for different heat engines. As you can imagine, efficiencies are very important to define when it comes to any system, because it gives you an indication of how good or how bad or how strong or how weak your system is. The first thing I'm going to say is that, as you can imagine, the generic definition of efficiency is what you want divided by what you give. And that applies to anything, really. So that's the generic one. Now, if you look at the sort of impossible heat engine based on the second law, this is the example which we know it's not possible under the second law. In this example, your efficiency will be 100%. Why? Because the efficiency in this case is Ws divided by Q1. Ws is what you want, and Q1 is what you give. And based on the first law, these are equal to each other, therefore this is 100%. But we know that that's not going to be possible, and based on the second law, and therefore this doesn't really exist. Now let's look at the things which exist. These are the three options, or these are the three different routes that we have for the heat engines. It's actually a good summary as well. We had the direct heat engine, which referred, for example, this was similar to the Rankine cycle. And please, you're going to be looking at, you're going to be using the word Rankine. Please do not write it with R-A-N-K-I-N-G. I've seen that, it's just so annoying and so wrong. So this is Rankine as opposed to Rankine. Refrigeration is, so these two are the reversed heat engines, and this is essentially our direct heat engine. You must be able to reproduce these figures at any time. So make sure you understand all the arrows and all the conventions, and you know the W and the Q1, Q2, etc. The reason why we have these three types of efficiency, or three types of heat engine in this case, is because each of these heat engines will have a different equation or different definition of the efficiency. So starting with the first one, I'm just going to number these so that you know what we have. This is the number 1, this is number 2, and this is number 3. And in each case, remember that we defined efficiency. You don't have to memorize these equations, but what you need to know is that efficiency is defined by this, what you want divided by what you give. Look at this example. What you want is this. I'm going to indicate this by red. And what you give is this, which I indicate by blue. So therefore you have WS divided by Q1. In the second case, I'm going to come back why we don't have eta, and we use beta in here. But anyway, for now, let's just look at the second type. What is, essentially what you want in a refrigeration is this. This is the important bit. In a refrigeration cycle, like the fridge in your house, you're interested in Q2. That's the heat which you get out of your icebox or from inside of the fridge. What you provide is WS in the form of the power that you supply to the pump in the fridge. In the third example, which is the heat pump, and it could be the ground source or the air source heat pump, what you are interested in or what you want is Q1, because you try to heat up your house, for example. So you're not interested in extracting heat. That is what you extract from outside, from the environment. What you're interested in is the amount of heat that your engine is supplying to your house. And what you give is again WS in terms of powering, providing power for the compressor in the heat pump. So, hence, we have these three definitions. The question, first of all, before we go any forward, before we go forward beyond this point, I just want to mention about this, which is essentially sort of good news. As far as the efficiencies for the heat engines are concerned, we no longer think about the sign convention for heat and work. So minus W plus W, which one do we supply, which one do we, we don't care about those now. Because you're interested in the absolute value of these, and then you're not going to get minus 50% as efficiency. So therefore, you don't have to worry about that anymore. Now, going back to the reason why we're not going to introduce eta and we use a different symbol for the refrigeration and the heat pump is because in the case of the refrigeration and heat pump, you'll actually find out that the efficiency works out to be more than 1. And because of the conventional definition of efficiency, you can't have anything more than 1 or more than 100%. Therefore, we write this as the coefficient of performance, which then it could be anything. It could be 5.6. It could be 5. It could be 1.8 or whatever that is. The coefficient of performance then is something that we use. That's a new notation that we use when it comes to these two heat engines. So this is going to be less than 100%, but these are going to be more than 100%. Now, we're going to be looking at some relationship between, or some extension of the equations for the thermal efficiency for these systems by using a combination of Q1 and Q2, because different questions will give you different values of Q1, Q2, W, etc. Therefore, it's important to be able to redefine these equations using different parameters. So, when it comes to the direct heat engine, the efficiency was Ws over Q1. Ws can be written as Q1 minus Q2, as you know. And that means that you can rewrite this as 1 minus Q2 over Q1. And of course, because Q2 is always bigger than 0, that shows why the thermal efficiency of a direct heat engine is less than 100%. When it comes to, so this was a direct, this is the reverse heat engines. When it comes to the refrigerations and heat pumps, we have Q2 over Ws. That's what we defined on the previous page. Ws, I'm going to rewrite it as Q1 minus Q2. In the numerator, I'm just going to introduce minus and plus Q1, and we'll see in a moment why we do that. That then will be equal to Q1 minus Q1 minus Q2. And then because Q1 minus Q2 is the same in the denominator, then I can rewrite as Q1 over Q1 minus Q2 minus 1. And I'm going to name this now as beta prime, because this is equal to Ws. So what it means, the reason why we've done this really is just to get to this point. B prime or B dash is equal to B plus 1. When I say B, I mean beta. Beta dash is equal to beta plus 1, which means the coefficient of performance for a heat pump is always 1.0 greater than that of the refrigeration. That's just to show. And you know, this is an important point to remember. So very quickly, I want to look at some of the corollaries of the second law. These are essentially, so there are 5 corollaries of the second law. We're just going to be looking at 3 of them. The first 2 are known as the Carnot Principles, and they are very simple and actually quite obvious. The first one is about the fact that the efficiency of an irreversible, so what we're saying here is that the efficiency of an irreversible heat engine is always less than the efficiency of a reversible engine. And that is quite obvious, right? The other thing is, the second corollary indicates that the efficiencies of all the reversible heat engines will be the same, provided that the temperature of the 2 reservoirs are the same as well. So as long as you're operating between 2 reservoirs with the same temperature, then the heat engines, regardless of what the heat engines are, they will have the same efficiency. The third corollary, which we're going to define here, is that the temperature scale may be defined which is independent of the thermometric substance. Do you know what the thermometric substance is? Have you heard of that? So anything, essentially, it's the materials or the material that we use to make thermometers. Such as, for example, mercury or platinum, for example. So the sort of materials that we use in order to make thermometers are what we know as the thermometric substances. So we can define a temperature scale which is independent of that substance. This statement, along with the previous two examples, statements, they have a very important implication. It means that as long as you have a reversible heat engine, wherever you have Q, you can replace it with temperature. So in all the equations that we've seen so far, Q2 divided by Q1, you can replace that by T2 over T1. Going back, for example, to the thermal efficiency of the direct heat engine, Q1 minus Q2 divided by Q1, which essentially is 1 minus Q2 over Q1, can be written as 1 minus T2 over T1. It's important because this means that in a lot of situations, you don't have to be given the value of the heat supplied or rejected. As long as you have the temperatures, and as long as your heat engine is reversible, then you can work out the efficiencies. This is just an extension of the other equations for the beta and beta dash. So just shows that wherever you have Q, you can replace it with T. And the reason why it's important is actually demonstrated in this example here. So I want to look at this example now, and then very quickly go through the instructions of for the quiz on Monday. So this example just shows two heat engines, exactly the same heat engines, the only difference being in the temperature supplied at T1. So the first one, so this is case 1, this is case 2, for example. In case 1, the temperature of the hot reservoir is 1500 Kelvin. In the second case, it is 1000. We have exactly the same amount of Q1 supplied to the heat engine. And what we want to find is, we want to find what is Q2, we want to find what is WS, and we want to find out what is the efficiency. We're going to do that for both systems. This one is for system 1. We're going to use the equation which we derived from the previous page, which was eta equals 1 minus T2 over T1. And your efficiency will be 2 over 3, around 66%, 67%. Your WS is just rearrangement of the equation, of the thermal efficiency equation, because we said that the thermal efficiency is what you want over what you give. And then you get 66.7 kilojoules. And by just knowing the fact that Q1 minus Q2 is equal to WS, by rearranging that equation, I can work out what is the amount of rejected heat in this case as well. Now, if I do the same thing for the second case, just want to zoom out a bit so you can see both. This is the second case now. We do exactly the same thing. What you realize is that now the efficiency is less, is actually around 50%, as opposed to 67%, which was in the first case. The amount of work which you get is actually less than this. This was 66.7, this is now 50. And the heat rejected is more. Now, we don't care much about the heat rejected in this case. What is important here is we had exactly the same two heat engines. The only difference was that one of the reservoirs was actually at a higher temperature. This now meant that your efficiency actually would be higher. This has very important implication. This talks about the quality. Remember we talked about entropy and I said this is an indication of quality? This is a higher quality system compared to this one. This is a lower quality. When you supply a system at a higher temperature, you're providing a better quality energy. And one thing which that means is that it's actually the conclusion of this really is here. When heat is transmitted across a finite temperature gradient, its quality is degraded. And I think the way to explain this is by looking at the equation which we defined on Monday. Q is equal to T dot ds. In these two heat engines, the amount of Q was fixed, right? So Q1, for example, was the same, was 1000. If this is fixed now, if the temperature is higher, which was in the first case, we know that ds, which is the change or the difference in entropy, has to be less to compensate for that. If the change in entropy is less, it means it's a better quality. And therefore, when you have higher temperature difference between the two reservoirs, you get a better efficiency. And the last point to mention here is that work is a higher quality of energy transfer than heat. Because when you provide work to a system, all of it can be converted into heat. But the reverse is not true. If you supply the whole heat to a system, some part of it actually will be rejected. You can't convert all the heat into work. Remember that container with the propeller? And I said, regardless of how much you heat up this container, you're not going to be able to rotate this propeller. But the opposite is not true. If you have the propeller and you start rotating it, you are going to convert all the energy into heat, and you're going to heat up the temperature of the container. So we're going to talk about this in the next chapter, which is our last chapter in entropy. But for now, let me just quickly go through